7.3 Bases and Dimensions. The content of 7.3 roughly corresponds to that of Chapter 4, where we talked about the bases and dimensions, and also 1.7, where we have discussed linearly independent vectors. When we talked about vector space, vectors of vector space, when the subset is finite, then the definition of linearly independent vectors and the linearly dependent vectors are the same as those in chapter 1 to 6, the same as those for Rn. When the subset is finite, when there are only finitely many vectors in the set, then the definition is the same as before. So let's talk about only the case when the subset is infinite. S is an infinite subset of a vector space V, and we say S is linearly dependent if some finite subset of S is linearly dependent. So that means we can find some vectors, finitely many vectors, that are linearly dependent. Then we say S is linearly dependent. And S is linearly independent if S is not linearly dependent. That means every finite subset of S is linearly independent. So if we draw from an arbitrary subset of S, it is linearly independent. Every finite subset of S is linearly independent. Then we say S is linearly independent. And S is linearly dependent if we can find some subset of S, finite subset of S, that is linearly dependent. Let's look at an example. S is this subset of M2 by 2. It has 4 vectors, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Is S linearly independent? S is a finite subset. It has only 4 vectors. So the definition and for linearly independence, the same as the case of Rn. How can we determine whether or not it is linearly independent? We form a linear combination of the vectors. Now each vector is a 2 by 2 matrix. Each vector a 2 by 2 matrix. We form linear combination. Each one is multiplied with a scalar, C1, C2, C3, and C4. And we set the linear combination to the 0 vector. For the 2 by 2 case, the 0 vector is the 0 matrix. And we see if this would imply all the C coefficients are equal to 0. If it does, then S is linearly independent. So is S linearly independent? If we add up the left-hand side, we get C1 here, C2 here, C3, and C4 equal to the 0, 0, 0, 0 right-hand side. So it does. It does imply that all the linear combination coefficients are equal to 0, and S is linearly independent. Another example. Let's consider S to be a subset of Pn. Remember, Pn is the vector space that contains all the polynomials of degree less or equal to n, and S has 1 power and the powers of x up to n. Is such an S linearly independent? To determine whether S is linearly independent, we form linear combination of the vectors. Now, each vector is a polynomial of x. We form linear combination of the vectors and we set it to 0, and we examine whether such an equation would imply all the c coefficients are equal to 0. And we see that on the right hand side it's the 0 vector. It's the 0 vector in Pn. So indeed, all the c coefficients are equal to 0 and S is linearly independent. Another example. S is the set. It has power of x, but it doesn't stop at n. It continue on. It continue on and on and on and on for all n. And this again is a subset of P. P is the vector space of all polynomials. Is such an S linearly independent? In this example, S is no longer a finite set. It is an infinite set. And to determine whether an infinite set is linearly independent, we draw an arbitrary finite subset of S and see if it is linearly independent, and this has to be true for every subset. So let's draw an arbitrary finite subset of S. So let's say we draw out k terms. We draw out k terms, and for the first one, it's the power of x raised to the power I1. The second one is I2, and the last one is ik. This is an arbitrary finite set, right? Because these I1, I2 are arbitrary non-negative integers. Is such a set linearly independent? Then this is a finite set. We can use definition of linearly independent set for a finite set, and we form linear combination of these terms and set it to 0 and see if it's equal to, and see if it implies all the linear combination coefficients are equal to 0, and we see that's indeed the case, right? So every finite subset of S is linearly independent, so S is linearly independent. Theorem 7.8 has a result that's very similar to what we had before, only that before what we had is the result for Rn. Here it's vector spaces. Suppose V and W are vector spaces, and T is a mapping from V to W, and T is an isomorphism. If V1 to Vk is a linearly independent subset of V, then their images TV1 to TVk form a linearly independent subset of W. So if we have some vectors that are linearly independent, their images are also linearly independent. We will leave the proof as an exercise. Basis for vector spaces. The definition is the same as before. A subset S of a vector space S is a basis for V if S is linearly independent and it's a generating set for V. For example, S is this set of 4 vectors, a subset of M2 by 2 that we have a symbol for. Is S a basis for M2 by 2? We saw earlier that span S is equal to M2 by 2. And this set is also linearly independent. It's linearly independent and it's a generating set. So yes, it's a basis. Another example. We have also seen this set before. S contains powers of x from 0 to n. And this is a subset of Pn. Is S a basis for Pn? This is a linearly independent set. And we have also seen earlier that its span is equal to Pn. So it's linearly independent and it's a generating set. So yes, it's a basis for Pn. For Rn, we have shown in chapter 4 that every 2 bases have the same number of vectors for the same subspace. And every basis has the same number of vectors, and that number is the dimension of the subspace. We will see a little bit later that's also the case for a finite vector space. Every basis for a given finite vector space has the same number of vectors, and that number is the dimension of the vector space. But here we need to do it in a little bit more roundabout way. We will first talk about coordinate and then prove every basis for the same vector space has the same number of vectors using coordinate. The definition of a coordinate vector is just like what we had before in 4.4 when we talked about coordinate of the vector in a subspace of Rn. Suppose beta is a basis, it's a finite basis for a vector space V. For any vector in V, the vector can be uniquely represented as a linear combination of the vector in basis B. That means that we can write it as a linear combination of the V vectors. And these linear combination coefficients are unique. If we collect all these vectors together, all these scalars together in one vector, this vector, we will use the notation V bracket and beta subscript. This is called the coordinate vector of V relative to the basis B. Remember the case when V is Rn, and we can write the linear combination as a matrix vector form. Then we can call this matrix A. This is matrix A. Then we can write it as AC, and this A matrix is invertible because these V vectors are linearly independent. And in this case, we can simply obtain the coordinate vector using A inverse C. There's a nice expression like this. But now there is some difficulty using such an approach with the vector space, because now these V vectors here are vectors in the vector space, and these V vectors could be matrices, they could be polynomials, they could be functions. So we no longer have an A matrix here. We no longer have an n by n matrix here. So the coordinate vector cannot be written in a simple form like this. So how should we go about this? Oops.
this one should be V here. Let us define something called coordinate transformation to help us here.
Let us define a mapping from V to Rn. The image of a vector V in V, vector space V, is the coordinate of the vector relative to the basis. So here is the vector space V, and this is Rn, and phi B, the mapping phi B, is a mapping from V to its coordinate. And this phi B is called the coordinate transformation of a V relative to the basis B. Let's have a couple of questions about the phi B. First of all, is phi B linear? So we are asking if we have a linear combination of u plus v, of u and v vector, the coordinate vector of the linear combination, would it be the same as linear combination of the coordinate vectors? For this, let's go back to the definition of coordinate vectors. And we can verify that's indeed the case. Yes, phi B is linear. Second question, is phi B onto? Onto means for all C in Rn, there exists a V vector such that C is the image of the V vector. And that's C. For any C vector in Rn, let's use these C vectors, use the coefficients in the C vector as linear combination coefficients to linearly combine the V vectors. Then the coordinate vector will be C vector. So yes, phi B is onto. Well, now you know what the next question is, right? Onto always go together. The question of onto always go together with the question of one-to-one. Is phi B one-to-one? Let's say we have two vectors u and v. Both of their images are C. So what does this mean? This means that if we use these coefficients in C as linear combination coefficients to linearly combine the V vectors, we get U. And in exactly the same manner, we can linearly combine the V vectors and we get V, right? So that's the definition of a coordinate vector. So we get V equal to U. And so phi B is also one-to-one. It's both one-to-one and onto. So that will make it a isomorphism. Phi B is actually an isomorphism. Does this mean V and Rn are isomorphic? Surely it does, because we have found an isomorphism, and that phi B is isomorphic. Phi B is an isomorphism from V to R is an isomorphism. So V and R are isomorphic. Now we are ready to talk about the number of vectors in a basis. V is a vector space with a finite basis, V1 to Vn. Then every basis for V is finite and contains n vectors. So that means every basis has the same number of vectors. Well, suppose that we have another basis. This A basis has k vectors and is another basis for V. So if we want to show the theorem, we need to show that this k is actually the same as n here. Because U vectors are linearly independent, so their images are also linearly independent. Because phi b is an isomorphism, so this is a linearly independent subset of Rn. So these k vectors are linearly independent, and they are a subset of Rn. But we know Rn can have at most n linearly independent vectors. So this number k cannot be larger than n, because Rn has at most n linearly independent vectors. Now let's switch the role of basis A and B. Phi A, now let's consider phi A. Phi A is a mapping from B to Rk, because A has k vectors, so the coordinate vector has dimension equal to k, so it's a mapping from V to Rk, and it will, because it's a basis for V, so phi A is also an isomorphism. And these basis vectors, they are linearly independent, right? V1 to Vn, they are linearly independent. So their images, phi A V1 to phi Vn, are also linearly independent. This is a linearly independent subset of Rk. There are n vectors here, and they are linearly independent subset of Rk. So we know n cannot be larger than k. N cannot be larger than k because Rk has at most k linearly independent vectors. So one says k is related this way, k and n are related this way, and the other one say the other way around. So combining 1 and 2, we get the conclusion n must be equal to k. Now that every basis has the same number of vectors, we can use this number to define the dimension of a vector space, a finite vector space. The dimension of V, denoted by dV, is equal to n, the number of vectors in the basis. We say a vector space V is a finite dimensional if V has a finite basis, or V is the vector space that contains only the zero vector. Otherwise, V is an infinite dimensional.